Alright, hello, my name is William Alden, and for our NAE project, we chose this topic about clean water, specifically water filtration. So here, I'll pull it up. We were given data on a filtration system that utilizes multiple layers in laminar flow. Laminar flow is when each particle of the fluid follows a smooth path. The first layer consists of nanometer scale channels to remove larger contaminants from the water. The data was obtained using a rough simulation to explore the flow of water molecules through these nanochannels, and I can actually pull up a picture of the diagram. So from right here, we're actually going to look at the bottom left of the position, and that's where we're going to measure the position of each molecule. This allows us to calculate the flow rate, and the flow rate is just the area times the velocity. So this type of flow is referred to as Poiseuille flow, which describes the pressure drop in an incompressible non-Newtonian fluid in laminar flow through a long cylindrical pipe. Essentially, some examples of this is just like drinking through a drinking straw, or using a hypodermic needle. So the biggest issues with filtration is the time it takes to filter the water. Viscosity plays a part in slowing down water molecules, which affects the flow rate. So using this data, we can see what molecules' positions and velocities are and come to a conclusion about what could be done to increase the flow rate, making water filtration faster and providing water to more people at a faster rate. So the graph trends will give engineers an idea how their filter is performing when they look at it. Since the filter uses laminar flow, the only component of position affecting the flow rate is the y direction. The slope of the line of best fit in theory for a working filter should be positive. So whenever I show you graphs like this and only one of them is actually positive, there's a reason why these are negative, and we don't necessarily know that, but I'll get to that here in a bit. So here, I'll start on the code. So the data file provided right here contains data taken at 26 different times during the simulation. The information for 300 water molecules is given at each time step. And there's also x coordinates, y coordinates, x velocities, y velocities. The first column of data contains just general information, such as the x and y dimensions and the time step from which it was extracted. So to improve the performance of the simulation, periodic boundary conditions are used. What do I mean by that? Well, if you look right here, when one water molecule flows out the right side of the channel, it's going to go back around and re-enter the simulation box on the left. So this is standard practice for these types of simulations. It's just so you can look at one area over and over and over again. So right now we're going to go ahead and get to the code. So if you look over here, the code initially asks the user for inputs, the length and the radius of the filter. I'll go ahead and just run the code really quickly. We'll start off with a length of 5, and these are in nanometers, and we'll do a radius of 7. So what this is going to do is it's going to come up with a bunch of different graphs. I'm going to pull those up and then hide those for now. We'll get back to those here in a bit. We did talk about one of them already a little bit. So it outputs 3 different flow rates for 3 different time steps, and that's what we're going to be looking at. There are 26 different time steps, but we're just going to be looking at 3 of them. Ideally, we could include all of the time steps and you could see the code, but to get an idea of the data we're given, we're just going to look at 3. So that is one of the limitations of this code with the time given. So we are going to start off, we have inputs, and we're going to pull data using XLSRead from our Excel function right here. We go down and we create variables, x coordinates, y coordinates, x velocity with y velocities. Using just the Excel data, we're pulling all the data out and naming it so that we can use it for our code. Another equation right here used for velocity is just the x velocity squared, y velocity squared, and take the square root. That's just basic physics. And so down here is the first time we use our function, is calc flow rate. And whenever you go in, it's just the equation for flow rate. It's pretty simple, nothing too crazy, but we do call on that function, and so that's what calc flow rate is. And then we just have some more mins and maxes, and so right here you can see where we actually have the 3 different time steps set up. So we are going to calculate the average velocity for the 3 different time steps using just the mean and calculating the flow rate from our function. And so that's just what this covers right here. We have the time extracted from the Excel data once again, and then using the y coordinates, which we created from the Excel data, we create positions and velocities. So right here we're actually going to start creating the first graph, and so this is of molecules 1, 2, and 3, it's going to end up looking like this. So let me just get that out of the way. So we go down and we create 3 different polyfits for each different section of the graph. So this is just the basic polyfit we've covered in class, the maxes and the mins, and we do that 3 times. And so we go down figure 1, which I just showed you, you subplot it, and it has all the fillers, the axis, the labels, and everything for molecules 1, 2, and 3. So now we go down and we're going to start on the second graph, and this is that was y position versus velocity, the y component of position versus velocity. Well, next graph is going to be the x component of position versus velocity. And so, let me get those out of the way. So we do the same thing we did above. We have the x coordinates and the x velocities, and we create different intermediate variables for those. And then we have 3 different polyfits for each molecule for the graph. We create the second figure using subplot and all the different fillers. And then lastly, now we have figure 3. What is figure 3? Well, we go down here and we can actually see the position versus the flow rate throughout the entire graph. And looking at this data without a trend line, I would not be able to figure out whether this was increasing or decreasing, and I could not decide on what the trend line would be. But thanks to MATLAB, we can utilize the polyfit function and actually see that there is a steady increase across the position as the flow rate as the position increases. And so that's just utilizing what we've already defined before. We polyfit, we have the x labels, the y labels, the axis, the equation, and down here that's where we get the output in the command window of the flow rate, is right here. So and I will talk about the problems that we did experience. So let's take a look at this y component graph right here. So during our project we did run into some problems because 2 of the molecules' trend lines right here comparing their position and velocity were negative. This showed that the molecule's velocity was decreasing when they were moving upwards in the filter. This completely goes against any theory because the molecule's velocity should have increased as they move upwards. The only time the molecule's velocity would decrease while moving upwards is if their path was above the middle of the filter. With more time and data, we would have been able to figure out exactly why those molecules' velocities are decreasing. And so, really, in conclusion, although we did not get the answers we expected, we did move in the right direction and made it easier to analyze the flow of molecules through infinite filter sizes at a set velocity. With more time and more information, such as the inlet and outlet pressure, and testing molecules at a variety of positions, we could have possibly found an efficient way to remove contaminants from the water. Thank you.